Hey students, welcome back. This video is on 3.4, which is the ideal gas law. And kind of without any further ado, we're going to jump right into it. I'm going to kind of skim over the first part of ideal gas law because in your last chem class, you probably had a lot of experience with it. And I'm going to spend a little more time on the stuff maybe you haven't spent as much time with. So let's kind of jump right in. Our ideal gas law, our formula is PV equals nRT. So P is our pressure. All right, and our pressure for the ideal gas law has to either be in ATMs, atmospheres, or kilopascals, kPa. All right, and that's because of this constant down here. We'll hit that in just a second. So then we have V, that's our volume. And this has to be in liters. Then we have N, this is our moles. And shockingly enough, it has to be labeled in moles. R is our gas constant. All right, R is our gas constant. And you have two choices here. I mean, there's a lot more, but there's only two on the AP exam that show up so you don't have to memorize them. And that first one is 0.0821. All right. This is the one that goes with the ATM liters per mole K. All right, because that's its label. Or we could use 8.314, and that's the one that goes with kilopascals per liters mole K. We'll actually use this 8.314 a little bit later when we do electrochem, but it'll have a little different label on it, but again, we'll revisit that later. So T is our temperature, all right, and that has to be in Kelvin. So remember, to get to Kelvin from Celsius, K equals degrees C plus 273, all right? You can add the 0.15 or not. All right, other things that hopefully you maybe learned in your last chem class or maybe just need a little refresher course on. We have STP. STP is standard temperature and pressure. All right, standard temperature and pressure. All right, and that is 1 ATM. Our pressure is 1 ATM, and we're talking about 273.15 Kelvin. All right, or 0 degrees Celsius, but since everything has to be in Kelvin for this unit, we might as well just go ahead and put that in Kelvin. Then we have molar volume. This is actually used a little bit more when we do stoichiometry, but it's good to introduce it here as well. And what molar volume says that 1 mole of any gas has a volume of 22.41 liters at STP. So at STP, 1 mole, and that's any gas, equals 22.41 liters, which will actually, like I said, it'll be more helpful when we do stoichiometry, but that's actually not in this unit. Okay, so awesome. So there are many ways that we can actually rearrange and use the ideal gas law, and this first one is density. All right, so the density for formula, and this has already been rearranged for us. So the only one that's new here is that capital M, and this is molar mass. All right, everything else stays the same. Little d is density. All right. So let's work a practice problem using this formula. So it says calculate the density of nitrogen gas at 125 degrees C and a pressure of 755 mmHg. So we're looking for D, so I'm going to put a question mark at D, just kind of working through our formula. We've got a P of 755. That is not a 5. All right, 755 mmHg. All right. Unfortunately, we cannot stick with mmHg, and we need to translate that just a little bit. So I always just go to ATM because to me it's the easiest, right? So 760 mmHg, 1 ATM on top. This will tell us how many ATMs we have. So 755 divided by 760. And I'm going to keep 4 decimals just to be sure that we're not rounding too soon. So 0.9934. Now we go to M, capital M. That's our molar mass. So we have nitrogen gas, and nitrogen is part of Hofbrinkel, or it's a diatomic molecule, which means its atomic mass, we're going to take 14.00674, and we're going to multiply that by 2, so we're going to get in the neighborhood of 28, so let's say 28.01, and that's in grams per mole. And we'll see how this all cancels out in just a couple of seconds. All right, and then we have R. Since we're in ATMs, we're going to use 0.0821, and that's atmosphere liters per mole K. All right, and last but not least is our temperature, and that's 125 degrees C, but we need to take that to Kelvin, so we're going to add 273.15. Sorry, I was getting real small there, and I just... this will be 398.15, right? Okay, so now we're ready to plug everything in. Okay, hopefully we can still see it. D equals, and we're going to take our pressure, 0.9934 ATM. I'm going to leave our units on there so we can see how everything cancels out. Then we have our molar mass, 28.01 grams per mole. All right. Ooh, got to the edge right there. Yikes. All right. Then we have over R, which is our gas constant. So we got 0.821. That's atmosphere liters per mole K. All right. And last but not least, we have our temp of 398.15 K. So if we cancel out things that we can, let's change colors there real quick. K, K, L. Oh, nope, L didn't cancel out, Griffith. Ooh, let's undo that one. Okay, how about ATM, ATM? We've got moles canceling, all right? And so we're going to be left with grams per liter, which makes sense because our density should be in grams per liter. Now we're ready to plug this all in. So we're going to take 0.9934 times 28.01. Then we'll 0.9934 times 28.01, and then we're going to divide by 0.0821 and divide by 398.15, and we should come up with 0.851 is what I got on my calculator, grams per liter. It looks like the book got 0.852, so we're real close there. All right, so that's our answer. And that was pretty easy. Do you have to memorize that density formula? No. You could actually use PV equals nRT and still solve this. All right, let's roll on and other things that we can do with the ideal gas law. All right, so we have mixtures of gases. All right, and partial pressure. So partial pressure is just going to be the pressure of one substance. And this is usually in a mixture, all right? So we're talking like, we could be thinking of like the partial pressure of oxygen in air. And then our Dalton's law of partial pressure is pretty simple. It says our total pressure is equal to the sum of the pressures. So however many pressures we have, we can just add them up and that will be our total pressure. Then we have our mole fraction, all right? This is the Greek letter chi, all right? All right, and what mole fraction, what we do is we take the moles of one over our total moles. And we can actually use that in problems to kind of answer questions and go from there. All right, so let's see if we can't work a problem. Actually, we have two problems that work this out because I was not sure if you guys had seen this before. All right, so we have a 1 liter mixture of helium, neon, argon, has a total pressure of 662 mmHg at 298. If the partial pressure of helium is 341 and the partial pressure of neon is 112, what mass of argon is present in the mixture? So we know we have a total pressure. We're going to start off by using Dalton's law. All right. And our partial pressures, so our partial pressure of helium plus our partial pressure of neon plus our partial pressure of argon would equal our total pressure. All right, so we know our P total is 662. We know our partial pressure of helium is 341. We know our partial pressure of neon is 112, and we're looking for our partial pressure of argon. So that's where we're going to start with our partial pressure of argon. So we're going to take 662 minus 341 and minus 112. This will give us our partial pressure of argon, which is 209 mmHg. So what we found is our partial pressure of argon, but we need to find our mass of argon. So we're going to actually now plug this into PV equals nRT and go from there. So P of argon is 209, right? But we want to convert that to ATM so we can use the correct gas constant. So we're going to divide by 160, and that'll tell us our ATMs. And that's going to give us 0.275 ATM. Then we have V, that's our volume, and we know it's in a 1 liter mixture. Do you think we need to worry about the fact that we have 1 liter of argon, but we also have other stuff in there? No, because the volume of argon is taking up that container, right? We said gases take the shape of the container, all right? N is going to be our question mark. That's what we're looking for because we're looking for mass, all right? We have R, our gas constant. That's going to be 0.0821. And then we have our temp, 298 K. It's already in K for us. So we're ready to now plug this in. All right. If we want to rearrange, we have N equals PV over RT. So we've got our P at 0.275. We have our V of 1. We have our 0.0821. And then we're going to multiply by 298. This will give us our N of argon, right? So again, we've got a little more work to do. All right, we've plugged that in. Now our N is 0.01124, and that's moles of argon. So we got one last step. Whew, lots of steps here to get to the end. And now we're going to multiply that by our molar mass of argon. 1 mole of argon has a molar mass of 39.95. And this will tell us our grams. And hopefully we get 0. Wow, that's not a 0. Okay, we'll try that again. 0.449 grams of argon. We're actually going to stop here on this video, and we'll pick up the rest of it in the next video. Okay, thanks.